What can we do with complex numbers? One answer is that they can represent transformations of the plane. In this short video, we're going to look at what the complex exponential function does to the plane. Our input z-values are on the left copy of the complex plane, and our exponentiated z-values are on the right copy. We'll observe that when you exponentiate a vertical line segment, that corresponds to the arc of a circle. The x-coordinate of a point on the vertical line segment corresponds to a point on the arc of radius e to the x when measured from the origin. And the y-coordinate of our input z determines how much we've rotated around the arc with respect to the positive x-axis. Now check this out. Input z with y values that are 2 pi units apart from each other gets sent to the same point on the circle. In other words, the complex exponential function is not one-to-one. That's important because the logarithm, which sends outputs back to inputs, isn't a function. But don't worry, you just do the same thing you did in pre-calc with the inverse trig functions. Okay, back to the animations in this video. Just remember, e to a negative number is a really tiny positive number. So now you see each vertical grid line gets transformed into a circle by the complex exponential. What's the complex exponential do to horizontal line segments? Well, points along a horizontal line segment are sent to a ray that emanates from the origin. The x-coordinate of an input z on the horizontal line segment determines the length of the ray, which is e to the x. The y-coordinate of an input z on the horizontal line segment determines the direction of the ray when we measure it counterclockwise from the positive x-axis. So the complex exponential gives us another way to think about polar coordinates in trig.